Hello friends, and welcome to this fourth installment of our webinar series on geology and the mining sector featuring Mrs. Francine Fallara. My name is Charles. I'm a communication project officer here at the FNQLSDI. Today we are going to cover cartography surveys. For those of you who missed our 3 previous lessons, they're available on our YouTube channel. Just look up IDD PNQL, the French equivalent of FNQLSDI. You'll find all 3 lessons in English there. Our next installment will be in 2 weeks' time on Wednesday, September 16th. We'll cover geophysical surveys. Housekeeping rules for today. If you have any questions during this presentation, just type them in the chat box on the right-hand side of your screen. I'll keep a tab of them, and Francine will cover all the questions at the end of this presentation. If you happen to catch this via replay and have any question as well, feel free to send us an email at info@iddpnql.ca. I'll pass a question along to Francine, and we'll get back to you to provide all that information. Without further ado, the floor, Francine, floor is yours.
So welcome back. Thanks for being here, and I'm glad to be back. And so as Charles mentioned, we're starting block 2. So the first lesson of block 2 regroups everything that we have seen within block 1. And we're going to see how to apply these notions within our geological maps. Just give me a second for now. So I'm back. Écran partagé. So, okay, I'm going to start the PowerPoint. Do you see my screen?
Works just fine.
It works? Perfect.
Yeah, we're good to go.
Good to go. Okay, so, and the mouse. So, exploring the geoscience, that's me, that's okay. Just going to move this around. So, starting block 2 for the mining exploration, the first step is for cartography surveys. So everything that has to do with geological maps and topological maps, and all the elements needed for making them, building them, and interpreting them. Sorry about that. So the lesson is going to be subdivided into an intro to the maps, the field observations that we usually use or put within our maps, the field data that we collect, and explaining how do we explain some of the geometries observed on the field. So the big question, what is a geological map? Geological maps is basically an interpretation of all the observations that we have taken on the field. There are different types of geological maps. These can be separated here. I've mentioned some main ones as geological history of an area, example for the land management and the land use for planning. For natural resources, we use those maps for development, protection, and extraction costs, like for characterizing energy, mineral resource, natural gas, coal, and oil. We also use them for the waste repository sightings. Geological maps have been used for a while for assessing groundwater, and a lot now within the municipalities for the quality and contamination risks of water, groundwater, and also for flooding. So we also have predicting hazards maps, including flooding, volcanoes, earthquakes, and landslides. And finally, for everything that has to do with civil engineering. So one thing you need to understand is that civil engineering and geological engineering work basically hand by hand. They consult each other's work for the buildings, the highways, and the infrastructures. So this is an example, as we talked in the block 1 lessons for the quaternary geology. So this is a good example of one where we could see both glacial and fluvio-glacial sediments. So the colors here within our legends would show any types of till, moraines, and things like that. And these illustrate well their extension on the land and their geometries. This is an example of a typical geological map, very simple geological map, and its structural map. So as we go today, we're going to learn the notions of looking at a 2D map. That means a plan view of a map. So it's getting into use when I'm going to say plan view or 2D map is like we are like a bird and we're looking down on the map on the land. So everything is flat. We have projected everything on the topo. So that's the thing we have to understand. Once we have this 2D map and we create what we call a cross section along the map, we can then view in 3D how these different units on the map are oriented and dipping, and also learning how they were deformed with different structural elements, either folds or faults, and how the beds, the different lithological beds are were deposited in the area and how they are now deformed and or altered. Another example here, as listed, is specialized team maps for predicting hazards. In this case, we have an example for earthquakes around the Charlevoix area. So in the background, you always have like the topological terrain where the geological information is projected on. So here it's a pseudo, it's not a 2D, it's not a 3D, it's what we call a 2.5D. That means we can see, looking down at the terrain, we can see the areas with elevations, but it's still on a flat view. Represented here are the lithologies with the major structures and all the measures taken live on the terrain that has to do with seismic activities. So the colors will represent also from blue to warmer colors, blue being the least active, to the warmer colors. So the legends are very important. We're going to talk a lot about that also today, everything that has to do with a legend, so that someone takes a map, a new map, and is able to find its way throughout all the elements on the map. A good example here of another predicting hazard is the flood risk areas. A lot of municipalities are now redoing these maps since the last couple of years of the floods going around. So these maps were done before very rigorously in the 70s, 80s, and then they were left for a while, and now people are coming back to them to organize the urban developments of towns. So basically what it shows is for medium to long-term areas where flooding could happen and about when in time. And finally, a good example for these maps also that are being used are for civil engineering. So civil engineering comprises buildings and infrastructure sites. So good examples here in for the mining industry is the Eleanor gold mine. So any mine, every part of a drift will be surveyed. So every wall, every drifting, every roof, everything will be a map and put back in 3D, so that we know all the areas where there are some fractures or zones of weakness within the rock, and to assure the security within the mine and to assure that drilling is safe for everybody. So these are basically updated mostly every day or as the drilling and or development is advanced. Another example here is the beautiful bridge of Mysticini that was built with the engineering Nordic structure wood from Schematic. And before building or creating a project like that, people have to know the soil, the ground. Is it safe? Is it solid? Is there some weakness? So these maps are used for that. Another good example is once you develop a mine, an open pit mine, or any kind of mine, you need to also know your areas, your different type of geology, and the ground. Always the ground, to know if it's solid, if it's gonna go through time and be able to be used for whatever reason we need to construct a building or whatever we need to construct. So these are examples. So now I'm going to go through what we need to see and how we're going to build those maps. So introduction to the mapping. Maps are basically communicating substantial amounts of observed geological information, and they are basically done so that we can give them to non-geologists, so that a non-geologist can use our maps and know exactly where he or she is standing. And what that person needs to know basically is, what are we standing on? So what type of rocks are we seeing? How old are these rocks? What are their composition? How were they formed? Is there any structural weaknesses around? Is it faulting, folding, any other geological processes? Basically, also what people want to know is there any potential for any mineral resource or geological hazards, and so on. So here what we see, we've seen this map already in the block 1 lesson, where the color basically identifies the different lithological units within the Quebec province. So since we cannot go out and we're doing this virtually, I am bringing you virtually on the field, and I want to share with you what a geologist is doing on the field, and the important part of our jobs when we are on the field. Basically, a geologist must remember that accurate geological maps are based on the geological work. What does that mean? It means that when you are on the field, you need to be precise, you need to be to have a good sense of observation, and you need to be able to document everything you pick on the field and be able to reposition it and to be further used for interpretation. So that's what it says here. It is pointless to make a detailed investigation of a specimen whose provenance is uncertain. So when you are on the field, you have your 2 feet on the rocks, you are taking some information, but if your map and whatever coordinates, whatever position you are taking is not right, it will not be useful in the future. So geologists, when they are recording observations, they use descriptive terms that are common to geology, and we will go through these today. The mapping is basically just a transfer of observations that is relevant for specific purposes from the field to our system. So just try to remember that any information that is taken in the field is like the raw data. It is taken down manually. It is drawn manually with a lot of schemas and things like that. But then this information has to be brought in digital softwares where we build the maps. So that's why the precision is important. And we use softwares like ArcGIS, MapInfo. We have an open source that is pretty much like ArcGIS, which is called QGIS, which is completely free. And these are used to bring in different layers defining different layers with different types of geological data so that it can be shared within any different types of departments and domains. So these terms are synthesized and rewritten into formal map descriptions, and we'll see these terms today. And we use each country and each province use national and international standard classifications, which exists, and the Quebec Ministry has a good book for that. And if you want a copy, I can send a PDF copy. So this is a basic example of a geological map. So what we need to understand also today is a geological map. You'll see it's a group of colors, lines, symbols, and things like that. But if you give a geological map like this to anybody without including a legend and the significations of your colors, your line types, and your symbols, nobody will be able to use it, unfortunately. As nice as your map can be, it needs to be well documented so that if you are not here, you are the person who took the observations on the field, you are not there when someone consults your map, all the information needs to be well documented on the map and on the legend so that anybody can read these maps. So that's what it says here. So basically, geological mappers work to illustrate the composition and the structural deformations of the Earth's surface and at depth. So they either show what's going on the surface, which we call 2D or surface data, and either at depth, which is either information within mines or from core samples being drilled. Interpretations of maps are done using different types of lines, symbols, colors to illustrate different traits about the nature and the rock distribution of the rock units within an area, and we'll go through them today. So this is just so that people understand, again, going through it one more time, the difference between 2D and 3D is very important in geology, very important in understanding geological maps. So on the first line here, we have our geological maps within different areas. And as you can see, they are 2D, they are flat, so they are two-dimensional. We can see through them different geological units that we, or phenomena that we saw in the first lesson. But to understand what's going on in an area, we need to know what's going on. We need to have a good 3D view, so a three-dimensional view, to be able to see the features, the complex features, the folds, the faults, and we need to see how the units are inclined or dipping. So good examples like we saw in the first block of lessons when we talked about horizontal strata. Well, horizontal strata is not too bad when we understand that from 2D to 3D, since they're flat bedding that are just superposed. But when it comes to domes and bassins, if we look at this one here, and we have no topological information and no other information on our maps, but just the color, no one is able to know if is this a mountaintop or is it a bassin. So is it a dome like we see here because we're looking at it 3D, or is it a basin? So that's when we need to add these information so that from our 2D paper, 2D maps, we can visualize in our head how these units are going. Same thing with here with the incline. I mean, all we can see that these are folds. We can see the different units, but we have no idea in 3D how these are going. In this case, it's called an inclined data, a strata or data or bedding, because we can see that it is not perfectly vertical, it is inclined, so we can measure this, which is called the dip, and we'll see this later on. So the first thing we do when we arrive in an area is it's important to do an overview map or schema or manual drawing, whatever you want to call it. So before going in on the outcrop and doing a zoom detailed map, we need to have an overview of what's going on in the region. So very important to have a notepad, any kinds of different kinds of pencils, pens, colors, whatever, and be able to take a picture, overall picture of the area, and to be able to represent it doing a schema. So as you see here, we need to bring this image, real image, into our drawing. So it is important to make everything that is different or differs from one side to the other within our drawing. So basically is to draw what you see. I had teachers, field teacher that used to tell us that. Draw what you see, and that's it. It's not magical, it's not difficult, it's just you sit down and you go one by one. And here, as we've seen in lesson 1, you can include everything we've talked about, like the change in granulometry of your rock. You can see here it's fine granulometry versus coarser granulometry. You see the color changes. You see some bedding lines here, so you know that your beds are horizontal. You see coarser or thicker beds, so you can draw there, versus here that are thinner. And all of a sudden, when you walk here, you can see a difference all of a sudden between this side, the left side, and the right side. So you know something structural happened, something very, something tectonic happened here to cause this drastic change from one side to another, because rock cannot change this drastically without a structural phenomenon. So here it was identified as a line, so as a fault. And then here on this side, we can see that our beds are no longer horizontal, right? They don't continue on the other side, and we can see some pseudo beddings that are more inclined, more steep, and this is what's drawn here. So basically, first approach is to sit farther from your area, have an overall view, draw that overall view. What we can do, we'll see that next week. Next week will be the geophysical surveys. Geophysical surveys here is a map, a 2D map of a geophysical survey in an area, are mostly used at first before you go on the field to do a first rough interpretation to see. They make out the main structures come out, and they make out some of the different lithologies, contacts come out. So you can roughly draw out the lines where there are some differences, some intrusions coming in, and some faults. And once you have these, and you are on the field, you can complete your map. So these, I just showed to show example that you can have within your geological map, you can have different types of layers based on the information you are putting on that layer. So the field observations are directly transferred from nature to map and your notes. So, and they are layered on various geological thematic maps to complete interpretations. And once you superpose these layers, it helps to have the final interpretation. So here again is an example. Once you are on the field, you go, you have your overall view. So you observe and you record your field data as selectively and systematically as you can. And important also doing that, knowing at which map scale you are gonna work. This we'll see a bit later on, and you'll understand why. So you compile as much information as you can, even if you are within an area and you cannot determine the rock lithology or name because it was too deformed or altered. It doesn't really matter at that stage. What matters at that stage is that you note everything you can see. Difference in colors, difference in rock bedding thicknesses, the rock's texture, granulometry, the difference in rock orientation, a sudden change between rocks, events. So you compile all of this within your notebook, and as accurate as you can of both the information you see and the location of that you take that information. And also you can complete your notes with sketches and photographs. Very important, because some places you only have a chance to go once and you cannot go back. So you compile all these field sheets, and these will be used as a visual summary or an archive summary of what you have seen. And using the mapping conventions, we document them on the maps. So these are used to produce what we call an accurate interpretative geological map using the conventional map symbols. And then once we are satisfied of our 2D map, we then construct a representative geological section across a map. And these, basically we do more than one, and they're spaced out. And once they are done, this will give us a 3D view of our area. So this one I zoomed in so you can see a better image of an area. You would arrive, you would take an overview of the area, and all of a sudden here you can see already, without even in not even a few seconds, you can see already some different areas, what's going on. If we start at the top here, we see that we have some layering that is like horizontal, and mainly the horizontal, and then there's a sudden break either in color, and sudden break also in the orientations of the units. Here they're horizontal or sub-horizontal, and here you can see that they are inclined, and the inclination is changing. We can see that things are being folded because we are able to follow units that are folded. We have the heart of a fold here. We see some change in granulometry, thinning. Here it's coarser. We have some boulders and things like that. So again, it's to have an overall view. Do take a first schema, drawing, sketch, whatever you want to call it, of the area as precise as you can. And once you are satisfied, you have your overall picture, you have your schematic picture, and then from that, using the terms that I will go through now, you'll be able to go back on the field and take all the information you've taken here and put it on your 2D map. So here I started with a simple one. Again, you have two colors. Two colors means you have two different units. The type of lines, I'll go through them afterwards. Type of lines will give you some type of information. And here on the background, the contour lines we have are the contour lines of the topographical map. We'll see that soon. And basically it's to drape the geological information on your topological map so that they are representative of the field you are studying. So basically, you need to understand your base maps and include the major landmark elements, such as the grid, as we see here. So the grid will include your coordinate system, the scale, and on the field, you need to adjust your compass for the area's declination. If not, your measures will not be good. You need to know exactly where you are. If you are taking your measurements either by your pace or bearing, there are some methods called the triangulate method to know exactly where you are. And of course, now we're using more and more the GPS. What we do is we do a traverses. So traverses are our main mapping techniques when we are physically on the field. Is just a walking along a predetermined route, plotting in the geology on the way. So what we do, example here, we can see that our units are trending Okay, one other thing I have to talk about is we need to know our cardinal orientation. So here, if I'm looking on a 2D map and I'm taking into consideration that my north is up here. By convention, if I don't see a north sign, our north is up. So if north is up, south is down, this side, the left side is west, and the right side is east. So I can see that my geological units contacts orientation are basically northwest, southeast. So we usually do traverses that are perpendicular to our rock orientation. So perpendicular means 90 degrees. So if my rocks are oriented this way, my traverses will be this way. So this way I assure to cut each unit at least once during my traverses. If I do it the same orientation of my units, I will never cut the different units. So that's the basic way to understand it. So the geology in between the traverses is interpreted. So in an area like this, where the geology is pretty simple, there's not much deformation, we wouldn't do traverses very close to one another, depending on the scale of our work. But let's say we would do them about 5 to 10 kilometers apart. Then if I had a traverse here, in the middle here, and at the bottom here, the information between two traverses would be what we call interpolated. That means if I have a series of points here, here, and here, and I know that I'm here, I'm within the purple rock, here I'm within the purple rock and the purple rock, so I know I can relate them together. So that's what it means. Interpolation means what we can extend into the area, even if we have not walked it. So using any clues to be surveyed, we can also follow the topography to make it logical. This method is used predominantly for reconnaissance work. Reconnaissance work is another word for surveying, and large areas of ground can be covered that way. What we are taking within our field notebooks are separated here. Everything that has to do with rock traits that we've seen within the block 1 lessons, so everything that has to do with the rock type, the mineral composition, the grain size, the color, texture, structural deformation, alteration, tectonic fabric, and so on. Any change, any differences that you can observe, you have to note it. The structural measurements, so whatever deformation you see, do you see any types of faults? Which types do you see? The folds, is it an anticline, a syncline, and then the measures you take on the field. Any type of mineralization that you see or that you think you see, or any alteration that would tend to show that we could have some mineralization potential has to be noted. And of course, like we just talked, we need to have sketches and photographs, because once we are back in the office or working on our maps, our digital maps, and we have questions, our photographs are our first way to go back on the field and be able to validate our interrogations. And that's also important for using. Once we are on our map, we're going to be confronted on the chronological evidence, as we've seen in block 1. And very important to know in time which element came first, which one is older and which one is younger, and the type of geological contacts. Sorry. So a good example here for a field map. Even if we have all our geological information, we cannot make precise maps if we don't use the topographic features. So what kind of topographic features do we need? We need to know where the outcrops, where the information we took on the field, where is it? So we need to trace these outcrops limits. We need to draw their real shapes. And we need to position on the outcrops wherever we took any measures as precisely as we can, and any place where we took some samples. Because if you take a sample somewhere and the analysis come back with anything interesting in gold or metals, you need to be able to know where it was taken if you want to go back and do some more investigation. So crucial, very crucial to know your locations too, and to be as precise as you can. So just to do a little sum up, contact exposure traced by a solid line, color-coded by lithologies, and abbreviated names for their lithologies and stratigraphic codes. We'll see that a little bit later on, but that's very important too. The structural data and any other field observations that were used, photographs, structural measures, samples with their location tags, and their ID key, which has to be unique. Whoops, we're not at the end, sorry about that. I'm gonna go, sorry about that. I'm gonna go that way. Have to remember not to do page down. Okay. So yeah, we're there. Okay, so I'm back. So the lines are very important. Different types of lines, very important on the map. Basically, I will include, if you want to have the ministry's guide, but basically the three major ideas you need to remember is between a full line, a dotted line, and a smaller dots and dashed lines. So the boundary certainty of an observation on the field has to be a full line. That means you saw it, you know exactly it starts here, it ends here. An uncertain observation on the field, that means you think it will be extended in that area. You're uncertain, but your level of uncertainty is, let's say, between 50 and 80%, let's say. So that would be a dashed line. And if you're really not sure, that means your uncertainty is lower than 50%, you really go with dotted lines. So same thing with a contact or any structural observation that you see. Certain is a plain line, uncertain would be a dashed line. And then when you see differences within a rock, all of a sudden there's a change from one side to another, a big difference of dip, like I've shown before. We call it a discordance, and so we do a wiggly line. Example of a field map that you can have. Field map can be as messy as they can be. You're on the field, you don't have a lot of space, you have a lot of observations, that's okay. As long as you have this on the side or anywhere else, but that you don't lose it, this is called a legend. So any color, any symbols, any type of lines you're going to put, any type of structural symbols, names, whatever you want, you need to have a trace or a document of this thing. So either in your notepad or directly on the map. So that once we bring it back in the office, the person who is in charge of tracing these contacts and creating all the different types of layers for the rock units, the structure, the alteration, and so on, is able to reproduce your map without you being there. So that's the key. Whatever work you take on the field, you need to think that you're not necessarily there all the time behind your map and explaining your map. So once you have your map, you have to be able to pass it on and that anybody can read your map. Reading your map, meaning to understand every element on your map. So that's why there is a standard way of building the maps. So the lithological codes should be clear. The map data is recorded in your field notebook. So again, your coordinates have to be clear. You need to be able to, if you're not there and somebody arrives, has to know what reference system are you using. We'll see them later on. What units are you using? Are you using feet? Are you using meters? Are you using kilometers? So it's a question of standardizing every observation that you are taking and documenting. The structural data on both your field map, as you see some structural symbols all the way around here, and your notebook. So you need to use your compass to transfer any direction readings and to be able to always have the strict minimum information, which is the type of structural data, the direction, and the dip. We'll see later on how to take these measures. So types of lines, as I explained before, types of symbols. So as we advance, you see that all this adds up. So to draw an appropriate symbols on map, you need to also know how to use your different colors. Most maps, but it's not a convention, a strict convention, but if you start, let's say, doing your contacts in black and your faults in red, well, you need to continue that. Because if you change somewhere else around here, the next day you're doing your faults blue, someone is going to be lost reading your map. So consistency is very important too. I'm showing here two different maps, same area. Map A, map B. Map A, I'm saying it's an accurate survey, and map B is poor. I'm going to go through the points why. Map A, as you can see, is more precise. The geometry of each element seems to be more real. At the bottom, map B, the elements all look the same. They're all blotchy. They're all like circular. Is it very representative of the area? I don't know. Here, it looks more representative. Some key elements, we see that the river is extended this way. We see the elements is following the river's direction. Here we have a blob. It could be that way, but usually it's supposed to follow the river's natural path. This one is drawn to scale. This one, I have no idea. We see different types of lines, as I discussed before. We see that this line here, this contact here, the geologist drew from here to there a plain line. That means, and he or she has all the information. We can see some measurements, we can see some observations, and the geologist was able to say, yeah, I'm able to, from here to here, I have all the information to back myself up. I am sure this line is here. From here to there, and the upper part here, we can see there is no information on the field. I'm going to start with this part. This part continues the line here. No, basically not enough information on the field, but on the outcrop here, we can see that there's a difference in his textures. So we can see that this side resembles this side, and the same for this. So that's why he says, well, I don't have enough information on the field, but I have some of them. So I have a certainty that is like higher than 50%. I'm pretty sure it continues here. So I'm just going to do some dashed line. Same here. And from here, decided to draw what we call a fold, as we've seen in lesson 1, but did it as a dash because there is no structural information or any other information that was taken on the field, but probably used this little outcrop here that we can see was folded. So again, from this area, this is good information, precise. So it was just what we call interpolated, interpreted in the area. Over here, the same outcrop. Look at the difference of the shape. So again, here we see that this is really not very representative. And so this line here is not representative also of what's going on, since it's supposed to respect this folding. Folding here is not just in area, it's extended around. So basically, from an accurate survey versus a poor documentation, these are the keys, the key definitions. So it represents contacts traced on the map as accurately as possible and to scale. It's also accurate placement of all the boundaries, as I've shown, and contacts due to accurate observations recordings. So we can see the areas where there are less. The geologist interpreted the area using the right lines. And also it respected the V's. The V effects is what we call, that has to do with valley and within hydrological areas like the streams and the rivers. For poor documentation, we see that the exposures here are too bubbly, what we call blubby, like everything is rounded, does not respect the outcrops, definitions or limits. They're not to scale. The boundaries are poorly placed, and also the interpretation is poorly done, and the V effect of the rivers are not respected. So that's a key part. I'm showing here with a picture now on the field to show, again, perfect or semi-perfect map versus something that is done like on the run and not very precise. So if you are on the field, the first thing you do, you arrive, you take an overview picture. Second thing you do, you take your notebook and you draw what you see. So drawing what you see, you could put your topographical limits. So here we have a shoreline with the water, contracts with the water and the outcrops. We have our shoreline here. We usually put a little stuff that we see on the top. So a little here, palm trees, some of the buildings, so we know where we are. The cliff is drawn here. The rock orientation, as we've seen here, and all of a sudden there's a break. So this break, we can see that the units are dipping more steeply versus horizontally, and some changes in thickness and things like that. So the map at the top has most of the things that we need. We have the scale, we have the orientation, we know this way is northwest. It says here facing north. We know this is southeast, so we're able to take that picture, take that sketch, bring it on the field, and we know exactly where we are. We know that the person respected the scale in the lateral as the vertical, because the person wrote no vertical exaggeration, so the scale this way on the vertical and the horizontal is the same as this. So the A is more detailed. The A has a scale and principal directions, and the A is more accurate and depicts the angular unconformity. Unconformity is just as you walk along, suddenly there's a break, there's a sudden change. That's what's an unconformity. In B, if I would take this picture and I had a pool of field pictures, I am not sure I would have picked this one, because it doesn't really resemble my field realistic picture. First thing, that's not precise. We have the beds here that are horizontal. The beds here are depicted as inclining this way. This one is not too bad. We have no idea which way we are looking. We have a little idea here. It is not very representative of what we see here. So keep that in mind. From this, I'm just showing you could have a very simple sketch, but this is like too simple. We need to fill in, yes, we have our topography area, which is good, but then we need to fill in what's going on in between the field, the simple topography, highs and lows, the basic cuts. We need to know what's going on inside with the rocks to be able to do our map. So the importance of visiting the outcrop, yes, it is important to have an overview, but then we have to go in and get all the details within the outcrop. So that's what it's saying here. You need to know exactly where are our faults, what is the attitude, the strike and dips of our rocks, and what kind of map of faults do we have, as we've seen in lesson 1. So another example here, also, thing you have to keep in mind is sometimes you have, like I said before, you only have one chance to map your outcrop because it's far isolated areas. Sometimes you have a chance to go back. So if you know you have a chance to go back, the first thing you do, first visit, put everything down that has to do with your position, the scales, the outer view I've seen here. So everything that has to do with the outer view, so that this picture can be fitted with this sketch. And then once you go back, you can add any kind of details that you didn't have time to go in. Even though your contacts are good, here a lot of measures were added that were missing here. We have some heights and lengths that were missing here, and also some difference in colors and glacial till, some quaternary geology that was missing here, and so on. So comparing the second sketch with the first, we noticed that the more realistic fault within the second one, see, there was like a kind of rough line here, but we didn't know what it was. When it was, now that it's defined as thicker, with an orientation, we know exactly that it is a fault. So that's also important. If you know that you are going back, then you can have different stages of your sketches. So basically what makes a map is your field observations and how you document it all. It is very important, as I said, everything that's different. Anything that you can sample it. Anything that you can describe it. Have a good way to localize yourself and your samples, and take as many measures with any instruments that you need that follow whatever study you need to do on the field. So another way to document, don't be scared to do first field interpretations. Even in 2 weeks, if they're not good, doesn't matter. This is how you progress in your interpretations, and this is how you walk from one area to another and see some similarities and some differences, and know, and then you will understand more and more what's going on. It's the first outcrop you visit. You cannot know the entire history of the area just by one outcrop. So you need to visit several ones, and it's an addition of all these outcrops that will give you all the hints needed to interpret your map. So going back, just one step back, topographic maps, why they are important and how we need to use them to project our geological observations. So again, here it's to understand the difference between two-dimensional 2D representations and three-dimensional 3D landscapes. So what do we need on our topo maps? Whatever we have that is our natural terrain, that would include your landforms, your peaks, valleys, ridges, domes, bassins, etc. Your lakes, rivers, your forested areas, everything that has to do with administrative zones, populated areas, roads, railways, and any other man-made infrastructures, your mines, dams, whatever. How the topographic system is defined within the country, within Canada. We have a system, the entire country has been divided into what we call the NTS, which is the system used and defined by the Natural Resource of Canada. So wherever we are within the country, we know from which map to start and to use the topographic data. So the example I'm going to give today is within the Abitibi area in Quebec. So using the NTS system, we know that the first big scale unit map is R032. So this I'm going to explain a bit later on. Just for now, also, the country has also been divided from north to south within major zones defined as latitude spans. So from the southern area, what we call the latitudes between the 40 north and the 68 north is the southern area here in yellow, which is followed here as the light blue Arctic zones between the 68 north and 80 north, and the high Arctic zones latitudes are between the 80 and 88 norths. So if I'm going to follow you through how to know how to identify your topographic system maps, so your NTS. So we want to work in the Abitibi area. We have what we know that it's within this box, so we know that we are falling within the 32 box. This is all based on the scale we are using. So this scale is our biggest scale, which is 1 to 1 million. 1 to 1 million scale, this 32 box has been zoomed in here, has been subdivided into 16 maps. These 16 maps are reduced down to a 1 to 250,000 scale. The separation always follow from the right to the left has been defined as our A, B, C, D. Then we go up, E, F, J, H. Go up, I, G, sorry with my French and English, I mix them up, K, L, and then we go up, N, N, O, P. This, if we choose this box here, and we zoom it again, we want to work within this box. It has been subdivided again into 16 maps, reducing the scale to 150,000. Again, we, starting from the right, down side, we have separated them and numerated them 1 to 16. So 1, 2, 3, 4, we go up, 5, 6, 7, 8, we go up, 9, 10, 11, 12, we go up, 13, 14, 15, 16. This has an extra separation too. The inner cross inside is to represent our 4 main cardinals, so north, south, west, east. And so the blocks have been divided into the southeast blocks, the southwest blocks, the northwest blocks, and the northeast blocks. So each of these 16 blocks have been subdivided one more time into the smallest scale, which is 120,000, and has been separated within 4 different maps to 120 scale. So if someone tells you I'm using the 202 map, you know, if you come back here, that it's within the northeast block. If someone says the 201, it's the northwest block. The 101, it's the southwest block. And the 102 is the southeast block. So depending on the different scales you are using, this is how we subdivide our maps and how they are identified. Within the Quebec sub-province, the same thing as I just showed you. I'm just representing them. So it's our NTS maps. So the big units, 32, 33, 34 are 1 to 1 million. Within these, They are then subdivided depending on the scale we are working in. So if I'm zooming in the Abitibi area, which comprises the entire block here, and this will go, this is the limit between Quebec and Ontario. So if we start again from the left side, we have our A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. And we can see that this goes from, we have Rouyn-Noranda from here till Le Lac Saint-Jean. And if we go up this way, we have Chibougamau. And we have a part of everything that has to do with the lower part, like Mistassini, and the lower part, Ismail is here. So just the limit with James Bay. So if I would ask, I would say to you, if I'm taking the example here, let's say Val d'Or. So I'm working within the 32. Val d'Or is here, C. And the subdivision of Val d'Or, where the point is 4. So we're within 32, C, 4. This is a good figure to understand that we need to absolutely use the topographic features within our geological maps. Because if we start here with this picture here of our 2D, it's a plan view of the Mount Fuji in Japan, Mount Fuji volcano in 2D plan view. If I did not add these topographical contour lines showing me that I'm going from 2,000 meters to 3,500 meters, I wouldn't know, with a flat view with the gray, I wouldn't know what I'm looking at. Is it a mountain? Is it a lake? Is it a basin? Is it just a flat surface? I would have no idea. So adding these lines, even if I'm looking at it top view, plan view in 2D, just having the topological contours, I know that I am looking at a peak. So if I'm representing the same image in 3D, this is exactly what we are looking at in 3D. So the topographic features are necessary to understand a 2D map. How we use these topographic features, all we see here is our contour lines from a topo. And all the topo, the basic thing a topographic map represents is the difference in elevation. Difference in elevation, we have our major marks. We see this one is 200 and we see this one is 300. Between this thickness and this thickness, we can count, we have 1, 2, 3, 4 lines. So with no legend, I know that my main separation is 25 meters. This is my traverse. This is the traverse I want to do, my geological traverse from A to A prime. I need to know how the land is going. Is there some elevation? Is there some depression? Is it a valley? Is it a dome? Is it a basin? Am I walking into a lake? I need to know all this stuff. The blue line here are our rivers. So I need to prepare myself the day before I go in the field. What am I gonna cross? So basically the easy way to do it is we take a piece of paper, we put it right under our traverse. We just put the dots that correspond to a new topographic phenomenon. So all the way along here, I'm over to the dot. I would include the river too. I would include a river, so I would know where is my river, how thick is my river, am I able to cross this river by foot, or do I need to contour? So that's very important too, because if I can see, if there's a big, huge river, there's no point in positioning my traverse here. I would be able to cross it anyway. So all this information I would go about like this, and that's all it shows here is that you place a paper along the profile trace line, which is our traverse, which is our A prime. You could call it A, B, as you wish. And then you mark each point intersecting a topo contour line with their elevation. So because I know this is 200, and this is 300, and I know this is going up, so I know I'm under 200 this way, and this way I am higher than 300. Next step is just to define a vertical scale, which is slightly lower and higher than the topo elevation. So slightly lower, I know this is 200, 180, 160. So I'm starting just a little bit under. So I usually use the same amount. If it's 20 meters, I usually go 20 meters lower. And same thing here. I'm gonna cross 300, but I'm not gonna go over 320, but I know I can go up, I can use this 320. So all I do here is this piece of paper that I put all my crosses along my traverse is I bring it down here. Once I have my vertical defined elevation, all the points that I wrote before with their elevations, I just draw them along the lines with their corresponding elevation. So 200, 200, which is this one. And then I move along, 200 again, 200 again, and so on. And this one is going down and so on. And then I just trace them as smoothly as in nature to represent how it's going up. I'm up the mountain, and then I'm going down the valley, and then I'm going to go up. And this also makes me visualize how my day is going to go about to go on the field, and how I'm going to, I'll know, I don't know, if I'm here by lunchtime, I'll know that afterwards it's going to go down the valley, down the river, and then I'm going to be able to go on the other side. So that's all it says here. And then from the previous steps, we mark all these, and then we connect them, and we have our smooth lines. So from there, whenever I'm going to take my geology, I know exactly where I am on my terrain, and then I'll be able to represent it in 3D on my cross section. Good example here, I did it on purpose to show this one, because if you're here and you're walking on your line, but you still don't know what's going on with your topography, and you're looking here in 2D, if I didn't have these symbols here, I wouldn't know. I would think maybe, oh, I have just one mountain, which is at 400. I wouldn't know that it's going down. I would maybe think it's a mountain, but these lines inside show that it's going down, so that it's a bassin, and we see that these are 400, 400, 400, 400, so that's our two peaks. So if you don't have this kind of information and these symbols, you wouldn't be able to trace that. So that's just an example to show that all of these information are used somehow before projecting our geology. The V's are the V's that are respected for everything that has to do with water. That's okay. That's okay. So everything that has to do with water. Again, if I only had the plan views B, D, F, with no symbols like this, I wouldn't know how my 3D representation is. I would have no idea. These symbols, we'll learn them later on, but this symbol to me is to represent that my bedding here is completely vertical. I know my river is here, so I know exactly that in 3D here, with this symbol, I know that this is going down completely vertical. With this symbol here, I don't have the dip, but I know that it's dipping that way. So that's why if I'm looking at this map like this, I know in 3D, I need to have my bed dipping that way. Same thing as this one, which is the reverse of this one. And this is going down, so we're going into a valley, and this is going up, so we're like a little peak, a little high, and my unit is dipping opposite side. So geological and topographic are two main observations we need to combine, and they need to work together. This is an example of my traverse. If I start from here to this point here, without the topographical data behind it, I wouldn't know how my day would go. But if I prepare it like this, I know I'm going to start in my highest peak in the morning. I'm going to go my highest peak of the day. Then I'm going to go down to this valley. Then I'm going to go a little bit higher. And then I have a huge valley, a flat. And then at the end of the day, I have a little mountain to climb and so on. And the geological information is going to be representative of the terrain. So it's going to be very precise. So once someone superposes the highways, the rivers, the hydrological system, and the geology, everything stands as one. Good example here of the top. A is your topographic features, and B is everything to do with your geological contour lines, your units, and things like that, and how they will be combined. So what features do we need now that we've seen, we've seen the first part I showed is the elements we need to take from the field. And then the second part I showed the importance of integrating the topography. So now I'm showing how we're combining these two. So first thing is to get your digital terrain model, which is your, in French or in English, is the digital elevation mapping, the DEM. We have a lot of free banks for that, the BNDT in Quebec or the USGS in the States. We can get these data for every elevation point. We have what we call the coordinate system, which is an XYZ, XY, X being your east-west coordinate, Y being, so your easting, Y being your north-south coordinate, so your northing, and Z being your elevation from the surface down or surface up. So this, you can work only with this data, your DEM data, or once you are on the field and you have additional 3D data, like from the drill holes, or any 3D data that can come from mining, you can also add these points which are really precise, because the DEMs are usually the best ones we have, are could be between 1 and 5 meters precision. But once you are on the field and you are drilling, and you know exactly where your drilling collar starts on the field, while the measurements of its XYZ is taken, so it's very precise. So we import the DEM as well as everything that has to do with road infrastructures, regional hydrography, the power lines, the railways, etc. And first thing we build, so this is our DEM, this is everything that has to do with roads, hydrography, and we build our digital terrain model, which is our DEM. So this is our first step, which is our topographic or topography surface. On this surface, we can see the natural elements where we have our highs, our mountains, our lakes, our rivers, and it's on that we project our geology. So what do we project for our geology? As mentioned before, but this is just a recall. Everything that has to do with mining infrastructures and developments, everything that has to do with surface geology, so 2D, everything that was compiled from historical work and or your field work. My advice is always to keep them separate. Always know which data is your compiled geological data versus your raw field observations that were taken on the field on your outcrops and that were not interpreted. So these are basically either points or contours. The positions of known showings like deposits and our mines. So you have a choice. You can put them either by type of mines. Are they gold mines, silver, copper, zinc? Are they active? Are they closed? Do you want their names? Do you want whatever their real coordinates? Do you want just to know, have more data also on your layers for their tonnage, productions, their reserves, and so on? So sky is the limit. It's the user's imagination limits that we can put on the layers layers can contain any information we want. The units are either shown by their lithology, so type of rocks, and or by their stratigraphy. Well, I'll show some examples later on. Stratigraphy meaning if you're working in a known area where the geology is well defined, and that you know already their ages and their groups, so you use that. You put the traces of the faults and the falls. You put the structural measurements and any assays, economical assays, or little geochemical analysis that you have from your field samples, and any other information that you can have, the alteration types, their intensities, the structural deformations and their intensities, any changes in the rock, colors, grain size, textures, etc. So this would be a good example from the first map that I showed you, that was the paper map, to once it has been brought into a system, a numerical system. So we have all our field of positions where the outcrops were, where the measurements were taken. We could have symbols where we took some different types of, I don't know, yellow for gold. We think there's gold. Orange for copper, and so on. So this map is what we have seen on the field, and it would need to be completed with a legend. This map is everything that has been taken on the field again, but superposed here on your topographic. So that's why you see some layering and some terrain forms or geometry. And once we have all this that are very well combined, this is how we can build our 3D image of an area. So what we need, another thing that is important to keep in mind, also for when you will build your legend, is always to know what are your youngest to oldest events, and separate them by type. Here I separated first my youngest to oldest events for everything that has to do with structures, fractures, so dikes, faults, lineaments. Everything that has to do here from youngest to oldest that has to do with geological formations, age, so which intrusions were first. So the first one, the second one, the third one, and age. So here I just resumed, I won't go reading all this, but I just resumed the fundamental elements that you have on a geological map and that you always need to have. So its title, its scale, the orientation, which way are we looking at, the legends we'll see a bit more. If you ever used some historical things that are not geological, and or geological, if you use the historical map, you need to put its reference. And if you need to put other reference locations, if you're near a city, the highways, and so on. Anything that is known as a mountain, whatever, a name of lake, the information, who did the map, who compiled the map. You can have a compiler, and you can have, the author is usually the one that did the interpretation, but you can have some help from compilers and so on. So anything that has been used other than the field data has to be added here too. The date it was published, because you can do a map this year and then give it to somebody else that will continue next year. So you have to make sure that you are using the right up-to-date map. The different scales. Scales are very important. What's your scaling work? What's your units? Are you working in kilometers, meters, miles, feet, and so on? Now I just want to teach the difference between small versus large scale. Example here within Canada. What you have to remember is here we're working at the scale of the country. Scale of the country, we cannot put a little detail here that's sitting here in Val d'Or or Chibougamau or any area you're working on. That's measuring a couple of meters, even a couple of kilometers, you need to have a bigger picture. So that's the same way as before, the first few pictures I've shown for the outcrops. You need to have an overview of your working area. So if you're working at a large scale of the country, you need to simplify your geology. Now I'm zooming in within Quebec. So if I go back, see the difference between here, there's less precision and colors than if I'm working just within the Quebec map. If I'm zooming in the Quebec province, you can see that there's more detail coming out. It's still a large scale because it's at the scale of the province. And then within the province, which is a large scale, I can say, hey, I want to zoom in. Here, example, I'm zooming in around the Chibougamau area. Zooming in around the Chibougamau area, I'm working at a smaller scale. Working at a smaller scale, I can define very thinner units and differences within an area that I can do at a larger scale. So that's the importance within how you need to know when you go in the field. Are you working for a regional map or are you working for a local map? You need to know that because you're not taking down the same information. Example of different scales so that you can see the difference from here at 1 to 50,000. This is the size of my box. I'm lowering to 1 to 100,000. This is the size of my box, which is roughly 4,000 square kilometers. I'm reducing to 150,000 to 120,000. So it gives you an idea of these different scales. From the first lesson, we've seen a lot of the terms that has to do with the structural, everything that has to do with fractures, faults, folds. Well, these each have their own symbols. And this are all within the ministry's guidebook that if you want, I'll send a copy. So it's so that anyone that sees any of these symbols can semi-automatically see in 3D what is going on in the area. The stratigraphic legend is when we are working within an area, often zooming out. Here I'm showing the entire Grenville province. So we know we have a good information of what's going on. We know exactly the name of each groups, their ages, their formations, and so on. So we are able to do a stratigraphic legend. So we know we're in the province of Grenville. We know their ages. We know their groups. If we're working in an area, a new area, this is not all known. So that's when it's the difference between a stratigraphic legend versus a lithological legend. If I would be zooming in an area, new area, I want more details, I would only use the lithological rock names, and that's it. So that's the importance of it. Other importance within a legend, a stratigraphic legend, is to know where are our oldest rocks versus our youngest rocks. So basically, even if we're missing space, normally the oldest rocks are the bottom, and we go up our legend and we go through our youngest rocks, and we basically put the main age stages and the type of rocks. Same thing here, sorry about that. Within the Quebec ministry, this is how they define either their stratigraphic using the name, abbreviations for the age of the rocks, and the name of the group, formation, complex, whatever, versus the lithological legend, which only states the type of rock, metamorphic versus intrusive here. We've seen this before. So how do we interpret the stratigraphic legends? This is when we are in control of our geological area, and they are done in advanced mapping, because we know where we are. Like I said, we know where we are with the ages, we know where we are in different rock formation groups, and so on. We cannot do this when we're working in a new area and we don't know the area. So that's the big difference. This, as seen in lesson 1, is when we're working only with the lithological legends. So the colors are important, and this is the basic ones used by convention, by the ministry, but you have to learn to read your legends because some private companies choose to use their own legends, and they mix things up just for confidential purposes. So they might switch some colors, some symbols. So that is why whenever you have a map, the first thing you do is always check the legend to make sure that you know which elements are stated, which colors are used, which types of lines are used, and so on. So basic example here, as I've seen in lesson 1, Quebec has been divided in 4: intrusive, volcanic, sedimentary, and metamorphic. So the colors are here. Types of map symbols. I will not go in details, but as you can see, each structural unit, not unit, but each structural type has its own type of lines, and each measurement has its own type of symbols too. Different kinds of faults I've seen in lesson 1, and there are different types of symbology. Always keep in mind, plane would be like the same type. Like here, there would be a strike slip fault. So you would go from confident to semi-confident to not very sure. Same, always the same way to do it. We can also add, we have the colors. We can also add within the boxes the rock textures. This is often done for sedimentary rocks and intrusive rocks and some of the metamorphic rocks. Seeing this, most geologists know that it is a limestone. This just indicates the bedding in the limestones. The conglomerates are basically with fragments, and this is just to show the fragments. The granites with the large crystals, and so on. So this is what we call textures, as we've seen. So this could be added through, because sometimes we have like 5 types of amphibolites in our maps, but the texture changes from places to places. So this could be added to differentiate these colors. So this is the book I'm talking about that resumes all these symbols and colors and norms. So basically a map on the field with all the observations that has been brought in, a software, and created layers by layers with its legend. Everything is in place. Everything can be turned off, on, with the basic names, and this is how to do it. This is just to understand, again, the difference between plan view and 3D view for a cross section. If someone is situated here on the top of the cube, top A, all you can see if you're walking here is you see these lines. But until you take some measurements, you have no idea how these units are dipping. So the dips, as seen if you were standing right here and looking this way, you would see that each units are dipping this way, and this would be the measurement of our dips. So if we look at the same block in a perspective way, depending on which side you are in, is giving you some of the rock's units orientation. I've seen the type of faults in lesson 1, the anticlines and the synclines. Same way is if you're on top in 2D and you're walking through, and depending on the bedding, if it's going out or in, you know that you are into an anticline or a syncline. And these, if you're walking on top, and once you have your measurements, you can draw them and represent them in 3D. So how do we interpret these structures once we have these all kinds of measurements, and how do we draw their axis? Here, example for folds. Well, we can see that these two are dipping towards the southeast. These two are dipping to the northwest. So we know there's a change in direction. So all we do is we draw a line this way and we go this way. And so we know that in the middle, we have our fold axis. Same thing here, we have a change in direction and so on. So this is it's a lot of time sitting and looking at the raw data taken from the field and interpreting how our objects are with the geometry and their orientation. So this would be the symbol to represent them. So we have our syncline with the arrows going in and the anticline with the arrows going out. So the difference again in 2D with an anticline and a syncline. So same thing with the faults. They can be represented on the maps so that we understand, looking from the top on a map, how these blocks were moved. Example here, we know there's a break because if we're walking here along and oops, all of a sudden we're not following on the other side, we know something has moved along this line. So as seen in lesson 1, we know that we can draw a line here to define a fault, and then it's just a question of, is it the hanging wall went up and the foot wall went down, so is it a normal fault or a reverse fault, and so on. So all the data from and all the measurements from the field, all the rock units from the field, it's all represented here. So the faults, again, it's a choice from line type, and line thickness and line color. This can vary a lot, and even though we have some measurements, we can see that the line is dashed, so it's not 100% sure there is a fault here. So maybe someone would say, okay, I have some measurements here, maybe I should go back and see if I can add some. This one is not too bad. This one I see there's practically no measurements. So it either was interpreted before going on the field using the geophysical maps, and that we'll see next week. So that's another thing to look at. Every time we have an element that has been interpreted, do we have some evidence that was taken on the field or not? And if not, we need to know how and why these lines were drawn. So it's an investigation, detective type of work. So every type of lines, fractures, folds, whatever, is how you represent them on 2D and how they really are in 3D. Sometimes it can become very complex, as you see. So big resume here is the difference to know how to interpret map view, plan view, and cross-section view. So an example here on this map, I did a A prime cross-section, and I can see in 3D how these units are acting up. The cross-sections, we use the abbreviation acronym called LOTS to remember to include everything on our cross-sections, which are our legend, the orientation of the cross-section, and the title and the scale. So the key to the patterns are used to identify each unit. So you need to, whatever legend you use on your map, it has to be the same on your cross section, or else people will be lost. So same colors, same symbols, etc. The orientation, we need to know which way are we looking. So here it's written we're looking west, southwest, east, northeast. So if I go back up on my map, you can say we're looking west, southwest, east, northeast. So that works. You can verify also this way. And finally, the title, what are we looking at? So usually we put as a structural cross-section, AA prime, looking which way are we looking at? And the scale, very important. So before checking the videos, I just wanted to make sure that people understand the terms strike and dip. Strike being also called direction. So it refers to the line which is formed by the intersection of a horizontal plane and an inclined surface. We'll see some diagrams. This can be easier to visualize. And the dip is just the angle between that horizontal plane and the inclined surface. So if I give an example like a roof on a house, example, simple roof, this line here is our strike direction. And I show you that north is this way. So this has to be a north-south direction. So the perpendicular line cutting along that strike direction, which is our roof incline, is what we call our dip. So the angle between these two lines will be the dip angle, so it is the measurement. So strike directions and dips can be measured on anything. It doesn't have to be just rocks, it could be anything. For the following slides, I always will put the strike direction in violet and the direction in orange. So if you keep this in mind, you'll never be lost. Example here, same thing. This time I'm measuring the same. So if I go back, this line here on your roof, where the top meets, would be the same as on my outcrop, this line here. This line here can be taken anywhere. I could have taken it here too. And then I measure a perpendicular direction to know exactly my dip, which would be my yellow here, as you see here. So we have a convention in North America, which is called the right-hand rule. Whatever you measure, your four fingers are used to be placed as your object is dipping or oriented or inclined, whichever term you want to use. The thumb is used to show the strike or the orientation, strike direction. So as shown here on this diagram, I'm going to turn myself like that. I can see my rock is dipping this way, so my four fingers are placed as it is inclined this way. And my thumb is used to show the direction. So if you remember that, you will never have any problem. So if you're looking at a map, this is the simple symbol used to show strike, which is the longest part, and the dip, which is the little part. And you need to put the measurements. So how would you go about? So if we go back just one, I said the four fingers are your dips. So if I go back in, if we're using the first one on the left, I see my little dot is going that way. So I would place my four fingers that way, and my little thumb would give me my strike direction. And here I just place on the background, so you're not lost. You have your cardinal. If you have your maps like that, so you know your north, south, west, east. And how you register your directions. If you use your compass, you know that your north, south, west, east. So you know your north is starting at 0 and it's going back to 360. So north can be written between either 0 or 360 as you choose. Your east is 90 degrees. And then if you continue on your compass, your south is 180 degrees. If you're going west, it's 270, and then you're going back to north. So you place your center of your compass at the intersection between the direction line and the dip right here. And using your hand to make sure you're measuring the right way, is you put your four fingers how it is dipping, so going to northwest, and your little thumb towards the violet line. So using your compass, you would be able to take your measurement here of your direction, and the dip would be the angle between the two. So it's as easy as that. And the convention for the strike direction, it's between, as I showed, 0 and 360 degrees. And the dip, since it's the angle between your strike direction and your incline, which is using the angle droit, which is the angle, the straight angle, has to be by definition a maximum of 90 degrees. So it has to be between 0 and 90 degrees. So this is how they are calculated. So example directly here on the field. So my incline, if I use this one here on the right, I can see that my inclines rocks are this way. So right away, I put my four fingers, I would sit my four fingers on that incline, and my thumb going towards you would be the way to measure the direction. So this is how all these measures are taken. And this is just a resume of what we just saw, from your pictures to your sketch to your measures. And this is what is brought back to your maps. So now we're going to resume all this with three little simple videos, but they're going to help you. And I've put some more that you can go and consult by yourself. So I'm going to switch to my videos. So the first one is just a little introduction of what does it mean, cartography, as we've talked today.
So it's the day before your mother's birthday, and you haven't bought her a gift yet. You know exactly what to get her: a candle from her favorite candle store. You drive to the mall, park your car, and walk inside. You then realize you've no idea where the candle store is. What do you do next? Ask someone for directions? Never. Your pride wouldn't take the hit. Wander around until you find the store. Sure, you could do that, but it could take a long time. You suddenly realize the perfect solution. Look at the map of the mall. Using the map, you can find the store in no time. Maps make our lives infinitely easier. From finding our way around town to finding a store in a shopping mall, maps simplify the physical world. It's not easy to make a map, however. There are countless measurements to be made, lines to be drawn, and all of it must be done with painstaking accuracy. It's no wonder the practice of map making is a complex one. Cartography is the practice of making maps as well as the study of maps. Cartographers generally either study the history of map making or use tools and techniques to make new maps. Many take on both roles. It's common for cartographers to have a broad knowledge base of both map-making history and the latest techniques. The history of cartography is incredibly complex. Some cartographers argue about the earliest known maps, and new discoveries are often made regarding major advances throughout time. The earliest maps may have been made as early as 7000 BCE. Some cartographers claim that the earliest map was of a city painted on a wall of a cave. Since then, maps evolved over time and had many uses. Some maps simply showed the elevations and terrain of an area, while others showed landmarks like mountains and rivers. Many early maps relied heavily on the positions of the sun, the moon, and the stars to determine direction. In particular, the North Star, Polaris, was used as an accurate indicator of the direction north. It has most often been a tradition in cartography to use north as the topmost direction on a map, though some ancient and modern maps put south on top. Cartography was advanced significantly in Europe during the Age of Exploration. For several hundred years, explorers developed new map-making techniques that enhanced accuracy. Of course, maps were still hand-drawn and accuracy errors were common. However, it was the goal of every cartographer to have as few errors as possible. Cartographers also began to develop new map projections, or styles of drawing maps that allowed larger areas to be represented accurately on a flat surface. These new projections were an important part of cartography because, after all, map makers are taking a chunk of a round object and displaying it on a flat surface. Modern cartography relies on computers to gather and interpret data about the Earth's surface. The most accurate maps of all time are now available with just a few clicks on the internet. Although these maps are easily available, cartographers still have a lot to do as they refine the interpretation of data all around the world. Let's review. Cartography is the study and practice of making maps. It has a very complex and storied history. Possibly dating back to about 7000 BCE, cartography has evolved through the ensuing years to be much more detailed and accurate. Today, modern techniques rely mainly on computers to map our world.
The next one is just to resume everything that has to do with the maps, symbols, legends, etc.
Just like your house key opens your front door, a map key or legend opens up a map. The map key is what gives you all the information you need for a map to make sense. But first, what exactly is a map? It is a way that we can show different parts of Earth in 2 dimensions. Maps can show large areas like the entire planet, or very small areas like your neighborhood. The purpose of a map is to show how things relate to each other spatially, but more often than not, a map also shows other kinds of information. For example, a map's purpose might be to show the pattern of the subway system in New York City, the number of people per country in Africa, the location of forests in Canada, or the location of monuments in Washington, D.C. These are just a few examples of the types of things that maps portray, but there are literally thousands of other things that maps can show. Being able to see relationships on a map is often much easier to understand than just a verbal or written explanation. This makes maps invaluable tools. But unless a map has a map key to open it up, it doesn't make very much sense. A map key or legend is included with a map to unlock it. It gives you the information needed for the map to make sense. Maps often use symbols or colors to represent things, and the map key explains what they mean. Map keys are often boxes in the corner of the map, and the information they give you is essential to understanding the map. Symbols in the key might be pictures or icons that represent different things on the map. Sometimes the map might be colored or shaded, and the key explains what the colors and shades mean. The picture here shows an example of a map key for a typical road map. Here is a map of Ruffy Lake Park in Melbourne, Australia. The 2 boxes in the upper left corner are the map keys. By looking at the keys, you can see clearly where the roads, grassy areas, rivers, and pathways are. There are also different icons used to show you the location of playgrounds, barbecues, parking areas, shelters, and toilets. Without the key to explain what the icons mean, the map wouldn't make a lot of sense. It's the map key that makes the map useful. This map has a different type of map key. The map shows the population of the United States and is color-coded. The map key explains what the colors mean. Green areas are the least populated, while red areas have the most people. Once you understand what the colors represent, it's easy to see where the most or fewest people live in the country. Maps are a way that we can show a 2-dimensional portion of Earth. In addition to showing spatial relationships, they also contain other information. Colors, shading, and symbols may be used on a map to show thousands of different things. A map key or legend is an essential part of the map. It explains what the symbols on the map mean and allows you to make sense of the map. Maps are very valuable tools that can be used to easily show things that would otherwise be difficult to understand.
And the last one is just a resume of how we interpret the geological maps. Okay.
When you think of maps, what comes to mind? Probably things like cities, roads, mountains, and lakes. Maps are very helpful to show us where things are located. There are lots of different kinds of maps: street maps, census maps, contour maps, and even geographic maps. Another useful type of map is a geologic map, which shows where geologic features are found. Don't confuse these with geographic features, which are things like valleys, oceans, and mountain chains. Geologic features are things like faults, silts, folds, and rock layers. And just like any other type of map, geologic maps have special symbols, lines, and colors that help identify each type of feature. But you probably can't make too much sense of a geologic map without knowing what each of these indicators means, so let's go through them in more detail. One of the first things you'll probably notice about a geologic map is the many different colors. These colors represent the different geologic units, which are simply the type of rock formation of a certain age. As you may recall, younger rock sits on top of older rock because the older rock was laid down first and provided a place for the younger rock to call home. So not all rocks in our geologic map are going to be the same age, even if they are the same type, and both age and type are identified by the different colors. For example, one layer of shale might be purple, while an older layer of shale might be blue. The color you see on the map represents which of these is present at the surface of the earth underneath the soil. Each geologic unit will also be marked by a set of letters. The first letter, which is usually capitalized, indicates the geologic period the feature is from. For example, J represents the Jurassic period, K represents the Cretaceous period, T represents the Tertiary period, and Q represents the Quaternary period. You could also have a combination of capital letters if the rock is from two different periods. Following the capital letter or letters are lowercase letters that tell us the name of that geologic unit or the type of rock. Names are often given to rock units for different reasons. It may be to identify where that rock was first studied, or it might be to describe where you would find the best representation of the rock characteristics. Other rock units are not named, so those are shown on the map with a lowercase letter that represents the type of rock. For example, S for shale and GB for gabbro, which are both types of rock. Something you might notice about a geologic map are all the different lines. Each type of line identifies a different feature on the map. For example, a thin line that separates two different colors indicates where those different types of rock come in contact with each other, which is called a contact. Faults are places where rock breaks apart and moves in different directions. They're represented on a geologic map by a much thicker line than that of a contact. Some of these faults are still active, like the very famous San Andreas Fault in California, while others are not. Folds are another kind of geologic feature you'll find on the map, and these are features such as bases and zones. Basically, folds are where you have a dip or a rise in the earth with a different age of rock in the middle than the age of rock on the outer edges. On a geologic map, folds are represented by lines that are thicker than contact, but not quite as thick as faults. Lines on a geologic map can also indicate where the land has been tilted. If you think of the Grand Canyon, you can quite easily imagine all of those exposed horizontal layers of rock. But sometimes the land is turned on its side by earthquakes or other geologic events. To indicate these tilted locations on a geologic map, we use a strike and dip symbol. This symbol has a long line, the strike line, that shows where the land is still oriented horizontally. And it has a short line, the dip line, that shows which way the disrupted ground is tilted. Finally, it has a number, the dip, that indicates in degrees how much the land tilts away from horizontal. Lines on a geologic map are not always solid. Sometimes they're dashed or dotted. Lines that are solid indicate boundaries that we know for certain, whereas dashed lines indicate boundaries that we are not 100% sure of. The problem lies in the fact that the Earth is covered with all sorts of things like buildings, roads, and mountain ranges that prevent us from always being able to identify the exact edges of a geologic unit, so we have to infer them instead. The more uncertain we are on the boundary, the shorter the dash in the line. For example, dotted lines indicate the greatest amount of uncertainty. We will never be able to find the exact edge of that geologic unit because it is concealed by another geologic unit. This sounds like a lot to remember, but don't worry. Like any good map, a geologic map will also have a key to help you identify and understand the different colors, lines, and symbols. This table usually presents the rock layers in reverse chronological order, meaning that the youngest layers are listed first and the oldest layers last. The key will also explain what the different types of lines represent, and any symbols that may appear with those lines, identifying things like the type of fault that may be present. Additionally, the key is the place where any other geologic information can key is going to be your best friend when interpreting a geologic map because it will be unique to each geologic area. So make sure that you take the time to look over. It will greatly help you understand what you're looking at. Maps help us identify where certain features are found. The type of map you use depends on the type of features you're trying to locate. Therefore, it makes sense that you would use a geologic map to show where geologic features are found. But in order to be able to use a geologic map, you need to be able to interpret it. Geologic maps are known for their distinct colors, each of which identifies a different type of rock from a certain geologic period. The letters associated with each geologic feature help identify the time period and name of that feature if it has one, or the general type of rock that's present if it doesn't have a name. Geologic maps also have many lines. The contact lines are those that identify the contact boundaries of each feature, while other lines may indicate features such as faults, holes, or areas of non-horizontal rock. The type of line, solid, dashed, or dotted, indicates whether we know the exact boundary, or if we're inferring it, and any symbols on those lines provide even more information about the feature to those reading the map. But the most critical component for understanding a geologic map is the map key. Here's where you'll find a list of what each color and line represents, as well as any other features or important information about the map that will help you with your interpretation.
So, for my part, it's finished. I don't know if you have any questions. Is there any questions for today's lesson?
Yeah, we'll give people in attendance a few seconds. While we wait, just want to remind everyone, once again, thank you for being present with us today. We were very excited to be back after this long hiatus. It was fun for us to get this going. If you have any, once again, if you have any extra questions, feel free to send an email at info@iddpnql.ca, and we'll forward those questions to Francine, and we'll answer either in the next webinar or via email. And once again, our next lesson will be held on Wednesday, September 16th, and we'll cover geophysical surveys. I think that'll be it for today.
Thank you.
Awesome. Well, thank you very much once again. Later.
Bye-bye.